Hi, my name's Owen, and I'm a software engineer working on Dagster. Today, I'll be walking through Dagster's new declarative automation system and how it can optimize how you update data across your entire data platform. If you're a longtime Dagster user, this system builds on the original auto-materialized policy abstractions to create a system that's more flexible, more predictable, and easier to use. But before we get into all that, let's talk about some of the challenges data teams encounter with other automation methods. Data platforms are often incredibly complex. Organizations can have hundreds or thousands of distinct data assets owned by a variety of teams. These assets typically exist in a complex structure of dependencies, where the status of any upstream asset can impact the decision of whether or not to execute. Crucially, you often have no direct control over those dependencies. They might be handled by another team or a completely external system. If upstream data is slow to update or never arrives, that has a direct and cascading impact on when downstream assets should be run. Historically, data engineers have worked around this in a variety of different ways. The simplest solution is to set up cron schedules at offset start times. So the first stage of your pipeline might run at 9 a.m., the next at 10 a.m., and so on. The core issue with this solution is that it ignores important dependency information. We know that the second stage needs to be run after the first, but because this link is not encoded anywhere in the system, upstream failures don't prevent downstreams from executing. The net result is that incorrect or incomplete data propagates through the rest of your data platform. This scheme is also an organizational liability. It becomes the role of documentation or siloed knowledge to keep track of the proper sequencing. This means that detecting these issues is inherently a manual process and makes debugging them a massive challenge. Another option is to group all of your assets into large, cross-cutting jobs that span team boundaries. This tight coupling ensures that upstream failures prevent downstream executions, but removes the ability for teams to operate independently. In essence, it couples together the outcomes of all assets in your graph together. Failures or slowdowns in one part of your data platform can impact unrelated computations that have been grouped together for convenience. This scheme also quickly breaks down as soon as you have assets that need to run on different cadences. Once again, you need to contend with dependencies between individual jobs. Something as simple as having a core set of assets run daily instead of hourly causes problems, as the more assets you lump into each job, the more potential dependencies you have between those jobs. Solving this issue often incurs further compromises, with a common solution being to simply give up and run more assets at a higher frequency than necessary, just to avoid confronting these interwoven dependencies. All of these workarounds impose a massive tax on productivity. While it may be simple to express and understand the behavior you want, implementing this behavior using imperative methods is generally too challenging to be practical. This impedance mismatch raises costs across all dimensions of a data platform. Slower dev cycles, more time spent debugging, less timely data, lower data quality, and wasted cloud compute costs can all be traced to inefficient and inaccurate automation methods. We believe that there's a better way. Dagster already provides a unified view of the dependencies and statuses of assets in your data platform. Why not use this information to make intelligent automation decisions? Declarative automation is Dagster's solution to do just that. It provides powerful, composable abstractions to describe when you want assets to run, as well as pre-built combinations of these building blocks to ergonomically handle the most common use cases. The result is an intelligent, event-based orchestration method that allows you to define when individual assets should be executed in a way that incorporates fine-grained information about the status of your data platform. From there, the system takes care of the complexities of monitoring that state and launching runs in response. This represents a new paradigm for automation, which treats the asset lineage graph as a key building block and allows you to tap into Dagster's wealth of information without any complex custom code. To make this more concrete, let's get started with an example. The first step in most data pipelines is to take some raw data and process it. For this example, we have raw event data that's uploaded to S3. This is done by an external process approximately once an hour, but the exact time isn't always consistent. We can track these updates using Dagster in a couple of different ways. We could pull the S3 bucket listening for updates, or we could have an external process send events to Dagster using our REST API. Either way, we want to get this data into Snowflake as soon as it's available, and then start processing it with our dbt project to make sure that stakeholders can see the updated data as soon as possible. A regular cron schedule just doesn't work here, as there's no specific time at which we can kick off our downstream computation that'll guarantee that our upstream data will be ready. We need to explicitly wait for that upstream data to come in. Dagster provides a built-in eager condition that you can attach to your assets and will handle this scenario, updating your asset directly after any of its parents update. To emphasize, Dagster already knows what data each asset depends on, and so there's no need to explicitly redefine this anywhere. All you have to do is say, update this asset after its parents update, and Dagster will know exactly what that means. This condition also bakes in a few common sense extensions. For example, if another upstream is currently in progress, it'll wait for that upstream to complete before kicking off, which reduces unnecessary computation. Again, Dagster has knowledge of both the dependencies between your assets as well as the status of them, and is able to use this information to intelligently react to events. Now, if we go to one of our Snowflake assets in the UI, we can see a detailed history of whenever it was or wasn't automatically materialized, as well as the specific reasons for this decision. The built-in eager policy is a combination of simpler conditions. When defining your asset, any of these conditions can be modified or removed to handle more specific situations. We can drill down into the specifics of why this asset was kicked off at this time, making it possible to understand the exact inputs that went into every automation decision. This precise explainability means that you never have to wonder why a run was or wasn't kicked off. Now that we've set up our data to be automatically processed and cleaned, we'll want to do something more interesting with it. We have a downstream machine learning team that takes this processed data and uses it to train a predictive model. Retraining this model whenever we get any new data would be unnecessary and would be far too expensive. We just need to update this once a day, but only once its upstream data is ready. To do this, we can use another built-in condition, on cron. You can think of this as a more intelligent cron schedule. Rather than kicking off immediately on a cron schedule tick, it'll wait to make sure all of its upstreams have been updated before moving on. No matter how many times the upstreams update, an asset using this policy will still just update a single time per day. And if some upstream data never comes in, then no run will be launched at all. This means that we don't need to create any imperative workflows or coordinate with the upstream core data team at all in order to schedule this asset. We simply tell the system how this asset should be updated, and it'll wait for the right time to kick off. To reiterate, when setting this up, all you need to think about is the cadence you want this asset to run on. You don't need to think about how to organize this asset into a job or how and when the upstream assets are getting updated. Each team is free to modify and optimize their assets without having to make large, team-spanning changes to keep everything in sync. By using this declarative model, we've avoided the pitfalls of traditional solutions. Cross-team dependencies no longer incur organizational costs, and setting an asset's cadence no longer needs to be a trade-off between cloud costs and complexity. So, to take a step back, the features you've just seen already represent a huge step up over the alternatives, but we've just scratched the surface of what's possible with declarative automation. Let's touch on another area that's traditionally challenging to manage. If we recall the original premise, we have some external process that drops the previous hour's worth of data into an S3 bucket. In many cases, it'd be useful to understand the status of each individual file, rather than treating the collection of files as a single unit. Similarly, we may want the ability to look back at the model training runs that we executed each day to understand how it's changed over time. We call these sorts of assets that operate over distinct slices of data partitioned assets. From a modeling perspective, Dagster makes it easy to represent these sorts of assets. All you need to do is apply a partition step to your asset, indicating how this asset's data is logically partitioned. In this case, we could partition the top part of our graph by hour and our machine learning model by day. Once that's done, we can see the UI update to track these partitions individually. From here, we can kick off runs of individual partitions or backfills of larger time ranges. But this higher fidelity modeling exposes new scheduling constraints. If we have, say, a daily partitioned asset downstream of an hourly partitioned one, you'd like to make sure that all of those hourly partitions are filled in before you kick off your downstream asset. It's not enough to just track the most recent upstream update. You need to have a full understanding of each individual piece of upstream data in order to automate this asset correctly. In legacy orchestrators, this sort of dependency would be a nightmare to track, let alone use to make scheduling decisions. But in Dagster, this all happens with no extra effort. You don't even need to update your automation conditions. These conditions are partition-aware and understand not just the dependencies between assets, but the dependencies between partitions of those assets. So if your upstream data fails to get updated for a few hours, you don't need to worry about downstreams kicking off with incomplete data. And as soon as that upstream data gets filled in, downstreams will kick off again. These partition mappings can get arbitrarily complex, but the core condition determining when an asset should be kicked off remains identical, regardless of what those dependencies are, meaning no custom logic needs to be added. Encoding and understanding this dependency information is essential, and declarative automation makes this easy. Finally, throughout this presentation, I've spent a lot of time talking about updating data assets, but that's not the only sort of computation that can benefit from deep knowledge of the status of assets and their dependencies. Historically, managing data quality has been a challenging thing to nail down. Of course, everyone wants to make sure that the data that goes through their pipeline is high quality, but this requires additional computation in order to determine if the data is high quality or not. This poses the question, when do we run that computation? Because data quality checks monitor the status of assets, they inherently exist in the same complex graph of dependencies as the rest of your data platform. Executing checks in the same pipelines as your assets can slow down or interfere with the core updates that you care about. But executing checks independently runs into familiar challenges as well. How do we make sure they only run after the asset it's monitoring updates? What if the check is expensive and needs to be run less frequently than the underlying data? These are the exact same challenges that asset orchestration runs into. The correct time to run these checks depends deeply on the upstream data dependencies. This means that in typical orchestration frameworks, these sorts of fine-grained decisions for these computations are generally too challenging to implement, and force users to gravitate to the same simple but suboptimal patterns. Declarative automation removes this trade-off. It can automate checks in exactly the same way that it automates assets. Checks that should always run when their asset updates can have the very same eager condition that we use for assets, and checks that need to run at a lower cadence can use on cron. And again, more specialized use cases can take advantage of the full range of flexibility that declarative automation provides. For example, you can set up checks to only run when the asset they're monitoring changes its definition, or put a rate limit on how often a check can run. Wrapping things up and zooming out, we've talked a lot about the challenges that traditional orchestration frameworks have with common everyday situations. We would argue that the reason for these challenges is that we've been using the wrong tool for the job. A tool that doesn't understand asset dependencies and their statuses fundamentally cannot effectively orchestrate even simple dependency structures. The result is wasted cloud compute costs on runs that never needed to happen, wasted dev cycles trying to implement and debug patchwork solutions, and data that's less timely and harder to trust. Declarative automation presents an alternative: simple, ergonomic APIs that make the common cases effortless, combined with the flexibility to handle any specialized needs. We're excited to have you try this out and see what it can do for your data platform.